videos. I am on the phet.colorado.edu website, and this little simulator here is called molecular polarity or molecule polarity. I want to describe what some of these features are and what some of these colors are and talk about what a little bit you can do and play around in here with. This is trying to show you how in a covalent bond, when you have atoms of different electronegativity, what kind of symbols and physical characteristics those atoms display. So in the standard default, we just have a very simple atom here, atom A and B. We don't have atoms for it right here. These green and yellow arrows, we can turn and play with it and kind of turn the thing around. This arrow right here is called a dipole arrow. You can click that on and off. I'm going to click it off for right now. So elements A and B, we can adjust the electronegativity value for atoms A and B. So right now, let's make them equal in electronegativity value. So we're not giving them, a value. I shouldn't even say value. It's not like it's 1.5 or 2.5. They're just relative to each other right here. So right now, atom A and B, because they're at the same tick mark, we could say they're identical atoms. This is like an iodine right here. We can even put it here and here. They're both in identical placing. So this is like an iodine molecule or an oxygen molecule. It's just identical atoms here with identical electronegativities. Now when atoms have, notice when I click on the dipole, that dipole arrow isn't present anymore because they have identical electronegativities. This chart down here is meant to show whether the bond is covalent or ionic. In the middle right here would be a polar covalent. So if I could rewrite this, I would say nonpolar covalent, polar covalent, ionic. So for example, let's shift. So right now, atom A and atom B are identical atoms with identical electronegativities. I'm going to increase the electronegativity of atom B. And two things shifted there, okay? So now this is very similar to, this is an ionic compound. We have a metal on the A atom and a non-metal on the B atom. They have very different electronegativities. And remember that metals and non-metals are on opposite ends. So this is like potassium, and this is like fluorine. Total opposite ends of the periodic table here. So they have a more ionic right here. Now, let's take that metal, and let's adjust this. So right now, this is letter B here, say fluorine. And letter A here is, say, potassium. Now, what I'd like for you to do is get out your periodic table and put your finger on potassium. And then as I move this cursor over, move your finger across the periodic table in the same direction I'm moving the cursor. So right about here, your finger should be on, say, arsenic or selenium, meaning it's more of a covalent bond. And now your finger is back on fluorine. So now we're looking at two identical atoms. So we have a very covalent bond with the dipole being gone right there. Let's reset this back to where they're both identical atoms in this less category right here. Let's put these in the middle. And again, note when they're both have identical electronegativities. There's no dipoles in the covalent. Let me explain what that dipole is going on there. Okay. So the dipole arrow, it is just a hieroglyphic shorthand to try to show which atom is going to have a positive charge, which atom is going to have a partially negative charge. So the dipole arrow has on its nook, on its knocking point, it has a little plus sign there. That's what that cross is supposed to be, a positive sign. And the arrowhead itself is like the negative sign. So you have a positive, negative right there. These symbols here on the ends of the atom, this is a lowercase delta, a Greek letter delta, and that's a negative sign. Notice that the arrowhead is pointing to the negative sign. Negative, negative, same thing. And this is delta positive. So this is how you would say this over the phone. A delta positive, a delta negative. And when somebody says delta positive, they are saying partial positive. It's not a full positive charge. We are talking about a partial positive charge. And this dipole arrow and this delta positive, they're always going to line up. So this is like repeating. This is like 6 eggs, half a dozen, saying the same thing here. I'm going to click those off for a second here and show you this image. So this image, if you think of 6 eggs, half a dozen, 3 pairs, we are trying to show you the same idea with charge. In chemistry, a red shade represents a negative connotation, a negative charge. A positive shade represents a positive charge right here. So this is a very negative, very positive sided molecule. The dipole arrow has the positive end towards the blue side, the negative end towards the negative side. The sigma delta, delta positive and delta negative are on the respective sides. And this is a very ionic bond. And their electronegativities are very different from each other. Again, this is like potassium and fluorine, very different. Potassium being very low in electronegativity, and fluorine being the highest in electronegativity. Now I'm gonna, you know how you had your finger on potassium and then moved to the left? Move to the right, excuse me. Let's do that again. I'm gonna move it a little bit. So I've moved a little bit down the lane here. Maybe I'm on chromium or iron. So we have an iron atom and a fluorine atom. Still a ionic bond, but there is less of a positive. So this is a little smaller in shape. This arrow is a little shorter, and this is a little less blue. Let's move a little bit further over. Now we're getting to like selenium, arsenic. So these delta negatives and delta positives are smaller. The arrow is shorter, and it's even harder to see the blue and the red, and see that this is getting closer towards the covalent side right here. This is probably a polar covalent, so to speak. And we keep on going to where they're identical. We now have fluorine and fluorine, and we see that there's no dipole arrow to show. There's no delta positive, no delta negative. This thing is all white around because there's no positive or negative end here. This electron density is trying to show a similar thing as the electrostatic potential. Now, electrons are negatively charged. So where we have more electrons is where it's going to be more negative. And where we have less electrons, it's going to be less negative. I'm going to reset back to potassium fluoride, where they're on opposite ends of the periodic table. A very ionic bond, because one's a metal, one's a non-metal. One has a very low, and they have very different electronegativities. These sliders are on opposite ends. See how the less electron density is on the partial positive side? See how the positive side here? This whole thing screams redundancy to me, where we have dipoles matching up with the partial charges, the electrostatic potential matching up with the dipoles and the charges, the electron density. They're all just different ways to help you visualize this. Now there's an electric field is the last thing I want to show you. I'm going to make these things identical, meaning like I want it to be a very, so I'm going to make these both very similar. And turn on the electric field. So when the electric field is on, we have a negative, we have a positive plate right here. We're not seeing like electric field lines right here, but we have this electric field right here. Though all of those things that we showed before, the bond dipole, partial charges, bond character, electrostatic potential, electron density, they're trying to show you visually with your somehow to spark your imagination to see where the electrons are, what they're doing, how they're behaving. The electric field is meant to show you how the electrons can influence the movement of a molecule. This molecule here, and let's just, they're equal, so let's say it's F2, chlorine. Okay? If we say take this atom here, A, and say change it to a, see how that thing kind of crooked back right there? Let me do that again. So it is aligning itself. We'll make that dipole larger. So you see how the dipole there has a positive sign on that side? There's that partial positive. That blue side right there. This molecule is going to align itself with the electric field because positives are attracted to negative stuff. Negative stuff is attracted to positive stuff. I hope this helps. Thank you.